Third type of distribution is Bose-Einstein distribution. In Bose-Einstein distribution, the particles are indistinguishable and there is no restriction in how many particles can occupy a given energy state or how many balls can occupy a given box. So particles are indistinguishable and any ball is equally likely to occupy any box irrespective of how many balls are already present in that box. Again, we consider n distinguishable balls to be distributed into m boxes. So we have n balls which are placed in a row and they have to be distributed into m boxes. We form m boxes by putting in m plus 1 walls. So these walls separate the boxes and form total of m walls. So there are m plus 1 walls which form m boxes. The first and second wall form one box, box number 1. Second and third form box 2. Third and fourth, box 3. And in this way, m and m plus 1 wall will form mth box. So there are m plus 1 walls and n balls. So we have put the walls in the space between the balls and get the balls into different boxes. A different number of different balls into different boxes. Now balls are indistinguishable. If you only exchange the positions of balls, then we will get no new arrangement. Even when the ball is transferred from one box to the other box, by just exchanging the position of the balls, we will get no new arrangement. To get new arrangement, it is easy to understand that we can move balls in the spaces between the balls. If we move the balls in the spaces between the balls, then we can get new arrangement of balls into these boxes. For example, I move this wall and place elsewhere. Now walls have been moved and now we get different arrangement of balls into these boxes. Only inner walls will be moved and not the walls at the ends. Walls at the ends must be kept fixed because they have to enclose the box. So only inner m minus 1 walls will be moved in the spaces between the balls to get new distinct arrangements. Now in how many ways we can move these walls in the spaces between the balls and get new arrangement? Before we tackle this question, let's also note that a box can be empty also. This may be represented by these displacements of walls. So here this box is empty. There is a simple way to understand how different arrangements can be formed. There are m plus 1 walls forming m boxes and only inner walls needs to be moved to get different arrangements. So we mark total of n plus m minus 1 places. N places represent for n balls and n minus 1 places for m minus 1 walls. So we have total of n plus m minus 1 places. So here out of these many places we put walls at m minus 1 places. Any m minus 1 places we put walls there and in remaining n places we put balls. We already have two walls at the ends. Two walls at the ends and m minus 1 inner walls have been placed in these places. So two walls are at the ends and in between these end walls we have n plus m minus 1 places. M minus 1 places have been occupied by walls and remaining n places will be occupied by balls, and in this way we get certain arrangement of balls. So here we can place balls and we have some arrangement of balls. Now the problem is here we have to only place the balls at different m minus 1 places out of n plus m minus 1 places that we have marked by horizontal lines. So out of n plus m minus 1 places, we have to choose any m minus 1 places for walls and put walls there, and the remaining places will be filled up by balls. So the number of different arrangements of balls in m boxes will be equal to the number of ways we can select m minus 1 places out of n plus m minus 1 places. In how many ways we can select m minus 1 places for walls out of n plus m minus 1 places. The number of ways of selecting m minus 1 places out of total of n plus m minus 1 is given by a combination formula. N plus m minus 1 c m minus 1, which I have written in this way. So in this many way we can select m minus 1 places for m minus 1 walls out of n plus m minus 1 places. Remaining places will be filled up by balls. So this is actually the number of ways we can arrange the balls into m box subject to the condition of indistinguishability and no restriction on the number of balls in a box. So this is the formula for Bose-Einstein distribution. If we select different set of m minus 1 places and put walls there, we have different arrangement. So problem is simple. Just choose the set of m minus 1 places out of total of n plus m minus 1, put walls there and fill remaining n places with n balls and get a distinct arrangement. Thank you.